Hello everybody, let us start today's discussion. What we are going to talk about today is a technique which was devised by Lagrange and which is useful in many circumstances. So we'll discuss a static case first. And remember, for the statics, if I am working in generalized coordinates, which means that to start with I have 3n coordinates, n particles, 3n Cartesian coordinates, and I have some, say, key constraints, and I get small n number of degrees of freedom. So let me just remind you, these are constraints, and this is degrees of freedom, right? So if I'm working in Cartesian coordinate, the principle of virtual work, which essentially describes statics, can be written as delta V equals 0, and that can also be written in terms of the generalized forces and the generalized virtual displacements. Remember that whenever I have one index repeated, it is already summed over. That was Einstein's summation convention, which we are using. Now, in case of generalized coordinates, again, all these different delta qi's, which are n in number, are independent. So this essentially implies that fi equals to 0. Right? And you immediately get the condition for statics. If I work it in any other coordinates other than generalized coordinates, and so let us take the example of the Cartesian itself. So I can still write the same principle of virtual work, and we wrote it this way with small f and the dxi. But now I is summed from 0 to 3n, and with this I have certain conditions. Plus there are these conditions which are 0. So this I am talking about, at this point I am talking about a holonomic constraint only. So I have to not only say that these are virtual displacements, so this is delta, but also I have to say that these displacements are made in such a way that the constraints are maintained. And because of that, I cannot say that fi are 0. Okay, I could say it here because all delta qi are independent, because I have these constraints, and let me count the numbers here. So I have n constraints. J can go from 1 to n. So there are n equations. Phi j equals 0. Phi j's are functions of all x's. And because I have this extra constraint equations, my delta xi's are not independent anymore. So I cannot say that fi are all 0. Okay. So that we said was the power of the generalized coordinates. But you see, it is not always that you will be able to reduce our system when you are practically solving a problem. It may not be always practical to write things in terms of generalized coordinates. Maybe it is not straightforward to think of in generalized coordinates to start with. Then what do I do? And that is what is given by Lagrange's method of undetermined multiplier. It turns out that it also can work with non-holonomic constraints, so it's even better. Our original formalism, we never talked about the non-holonomic constraints. So now, this can, as I said, can work in many different situations. Let us start with the problem of statics, because that is what we are discussing here. So let me define for you this problem in general first, and then we'll mostly look at a very simpler example, because that is always easy to do. So I have the potential, and I am talking about monogenic forces, and also I have a potential defined, which is function of this So these are neither the Cartesian, neither the generalized. This is something in between, if you wish. This n, so n is the number of degrees of freedom. But when I define the potential, it is difficult, say, for this particular problem to write down in terms of only the number of degrees of freedom. So I have also the constraints. So which means that I have not reduced my dimensionality of my space. Okay, so I am still left with k constraints. So one example can be that I have written down the potential in terms of the Cartesian coordinate systems. So the potential is a function of x, y, and z. But say that, so the old example that you're always taking, so say x square plus y square plus z square equals r square is my constraint. So that means that because I have this one constraint, n equals actually 2, and I have one constraint k equals to 1. So I am writing, so these u's are basically x, y, and z, all u's combined, and these two are like you can choose any two of them as the n degree of freedom, and I have one extra from the constraints. So that is the case that we are talking about. Now we can say, so along with this, I also have auxiliary conditions, which are the constraints. These are sometimes called auxiliary conditions also. So let me write it that way. And these are, I am writing them as polynomic constraints, where this is phi I as a function of all the coordinates. So un plus k, and I have polynomic, so they looks like this, right? So now, what does principle of virtual works tells us? What does it tell us? It tells us delta v equals 0. And as I said that v is a monogenic, so this implies that del v del ui delta ui equals 0 along with so I also need to include the constraints. And you see that we said that if I am not dealing with generalized coordinates, I have to say that it has respected the constraints, my virtual displacement respected the constraints, which essentially means that delta phi is 0. So because of the virtual displacements, I should not be able to see any change in phi. And what does that give us? That gives us del phi del ui delta phi I equals 0, right? Okay, so I have these two equations, and here I have chosen, there can be k such constraints, but just for understanding purposes, so let us choose, for understanding purposes, let us choose k equals to 1. Otherwise, it will be extraordinarily complicated to start with. So it is better to work with something we can understand easily, and then we can generalize. Okay. So for understanding purposes, let us choose k equals to 1. So how do I write that? So so let me rewrite things again. So I have v. So I have v, which is a function of u12. Now it could have been un, but I have one extra, and I have phi. I have only one phi because I have k equals to 1, which is a function of, again, all these coordinates. And the principle of virtual works gives me two things. One is that delta v is del v del ui delta ui, and delta phi is del phi del ui delta ui. Okay. So it gives me these two things. Now, one thing you may have already understood from our previous discussion when we are saying that if I choose any coordinate system other than the generalized coordinate system, the coefficients of delta xi cannot be considered as generalized force and they are not independently zero. So here also we don't have, remember that we don't have del v del ui are not zero. So here comes the technique of Lagrange. So what he said is the following. He said, okay, so this is equals to 0 and this is equals to 0. See, if I construct this delta v plus a lambda which is a function of all the coordinates, and at this point it is undetermined, so it's arbitrary. So I multiply this with delta phi. What should this be? Well, this is 0. Whatever you multiply with 0, it always remains 0. So this should be 0. And now if I write in terms of the partial derivatives, so I get that del v del ui plus lambda times del phi del ui, this times delta ui is 0. If I do this, then let us ask the question what happens. So first, how many equations are there? I have n plus 1 such equations, right? Now if I would have had k equals to more than 1, so I will have n plus k equations and I will have k lambdas, right? So let us work with k equals to 1 for the time being. You can figure out what will happen if k is not equals to 1 but some larger number. Now I have to fix one lambda. I have n plus 1 such equation. I take one of them, any one of them. You can choose the last equation. So take the last one. Okay. So I take the last equation. The last equation will be del v del un plus 1 plus lambda del phi del un plus 1 and delta un plus 1. So what do I mean by last equation? Is the last term in that equation. Then is the last term in that equation. And remember, lambda is a function of all these coordinates and it's undetermined. So I fix lambda by setting this equals to 0. So lambda becomes minus del phi del un plus 1 by, del v del un plus 1. Let me correct it. By del phi del un plus 1. Okay. Remember that these quantities are known because I know what is phi and u in terms of all the coordinates. Okay. Once I set this becomes 0. Once I set this becomes 0, right? So I get an expression for lambda. So now I can write the rest. So rest of the n terms now can be written as del v del ui plus this lambda is what is coming from there, so you put it there, del phi del ui. Now ui goes from 1 to n now, not n plus 1 anymore. The n plus 1th term we have already set to 0, right? Now you see, okay, first of all let me tell you, if k is not equals to 1, I will need k lambdas to be fixed, and once I have fixed k lambdas, I can put them back here and then this will still work out. Now, once I have done this, now what do I have? I have the principle of virtual work written in terms of n coordinates, and n is the degree of freedom. Remember that n is the degree of freedom. So now it is quite clear that this quantity is equivalent to and actually is the generalized force. This is the generalized force and all of them are equals to 0. So that's how I now, using the Lagrange method of undetermined multiplier, now which is determined by this, I can figure out what are the condition of static for statics. Okay, so this is a very powerful tool in that sense. And if you look at this stage, what it essentially does is, is to change V to an effective potential which is just V plus lambda j phi j. Okay, and lambda j is determined as before. Okay, so if you do these substitutions, this j stands for, so j belongs to 1 to k now if there are k constraints. For our case, it is just lambda phi. So then you will get all the that's the same equation if you do the variation now. Okay, so this is the case for statics. Now you see, because the expression is written in this way, so this is the final conditions are written in that way, which is del v del ui plus lambda, and then the derivative of the constraints with respect to the coordinates. So in this particular case, I have rather a holonomic constraint phi. If I did not have a holonomic constraint, the constraint would be written in terms of non-holonomic, that is non-integrable terms. So the constraint I will write like this, right? Aij du I plus aij du equals 0 for j constraints. So j goes from 1 to n, 1 to k. Now for the virtual displacement, obviously this will be aij delta ui equals 0. So this will be the virtual displacement because of the constraints. So this is equivalent to what I had before here, this. And you see, for this non-holonomic constraints, all that I have to do is, so this is case non-holonomic case, all that I have to do is, I have to change this equation. Instead of phi, I will have to write it this way. This is equals to 0, and let me put j over back here, which is the number of constraints. So this is the non-holonomic case. This is the holonomic case. Now this method is particularly useful when you are working out problems, because you may not need to now think about a very complicated coordinate system, which is generalized coordinates, but you can work with what you think as a simpler coordinate system. The particles may not think it as the simpler. For the particle, generalized coordinate is the simplest one, but your personal choice can be any other coordinate system, and then you use the Lagrange method of undetermined multiplier to solve the problem. Okay. Now, this is the case for statics, as we are discussing. Now, let us come to the case for the dynamics. For the dynamics, so this is dynamics. The monogenic function, and we are working now in terms of Hamilton's principle. So I have L, which originally is a function of all these, as just exactly we were writing earlier, un, and say I have then n plus 1 to k, n plus k. So all these coordinates, this n is the degree of freedom, and I have k constraints, so I have total n plus k coordinates. It can be equals to 3n, not necessarily. Okay, what do I do? So I start by defining, I change my Lagrangian to L sum L prime, which is again nothing but L plus lambda j phi j. Okay, and I'll not work out, but you can go through the exact same logic as we did before, and the modified Euler Lagrange equations will be the following. This is my usual celebrated Euler Lagrange equation. All I have to do is I have to add lambda j del phi j del ui. Okay, one thing I forgot to tell you here is that this part is the constraint forces. So del v del ui gives you the external force, lambda aij gives you the constraint force, or this also the same thing gives you the constraint force. Because you are working in a coordinate system where you have not restricted all the constraints, you can now see the constraint force in action. Now this is the case for holonomic. Remember how you fix lambda j? You fix lambda j exactly the same way. So you go to the excess coordinate system, and for that excess coordinate system you say that lambda is the del v by del u n plus 1. That is the first lambda, del phi del u n plus 1. If you have two lambdas, so you go to n plus 2, because then it will go to n plus 2, and three constraints you will go to n plus 3, etc. So you'll get all three lambdas. So this holonomic case, the non-holonomic extension is fairly straightforward. Now instead of the derivative, we will just write the coefficient. Okay, so this is the Lagrange method of undetermined multiplier. The actual method is very simple. So what you do is you have, so let me just outline the method a little bit here in more abstract form. I have something equals to 0 subjected to a constraint which is some other things equals to 0, some other things equals 0. Okay, So what all you do is you write them together. You write this something plus some lambda times this something equals 0 and fix lambda in terms of the x coordinates. That is all the Lagrange method of undetermined multiplier is. And these are the results. So these are the fruits of those methods. Okay, so I thought it will be useful for us to look at an application and let us apply it to a case which we have, a problem which we have done so many times, and you know very well what the solution is. But it will give us an idea how it works out. And we will also see a little bit of trickery in this case of the problem. The problem is of a simple pendulum, as familiar problem that can be. So I have the pendulum, say, somewhere here at this point. This has a bob of mass m. This angle I call phi, the length of the string L. And so how to do this, work out this pendulum? Well, so let me first do not with Lagrange method of undetermined multiplier, simple. So I can choose a coordinate system. In this case, I choose the origin here. I choose a spherical polar coordinate system. So t is equals half L squared phi dot square. And we know that rho equals to constant, so it will rho dot is 0. So I can directly write t this way. And the potential energy will be minus g L cos phi. This I am not going into detail because I am pretty sure you know this very well. Okay, so gl cos phi is L cos phi is this, it is negative, and then I have minus g. So I construct the Lagrangian half L square phi dot square plus gl cos phi. And then I get the Lagrange Euler-Lagrange equation d dt of del L del phi dot equals del L del phi, which will essentially this time will, what will it give me? Del L del phi dot will give me L phi dot, and then I am doing a d dt, so L phi dot double dot, and this will give me a minus sine phi, so this will be gl sine phi equals 0. Now this is all we know very well. Sorry, this is L square. So you know this very well. One L you can take out, but and you can approximate sine phi to phi for small oscillation. You get the simple harmonic oscillators. But that's all right. That we all know how to solve it this way. Just to demonstrate the Lagrange method of undetermined multiplier, let us solve it in a different way. And again, I will do half of it, and the rest of the algebra I will do. So what I do is I say that okay, it is oscillating in 2 dimensions. Why don't we consider the coordinate of this as x and y? Okay, so this is length again L, and this is a mass m, and this is my origin. So my kinetic my kinetic energy is half m x dot square plus y dot square. Let us choose m equals to 1 just for simplicity, nothing else. T equals half x dot square plus y dot square. And what is my v? Is minus gy, right? And then I have a constraint. Now I have a constraint because I have 1 degree of freedom and 2 variables. The constraint is simple again, x square plus y square equals L square. Okay. You see, actually I have two constraints. The other constraint is z equals to 0, which also z equals to 0 in all time, which also means z dot equals to 0. So there will be no z dependence in anywhere. So I know that I am using this constraint, but that is already used. So this constraint is not used up yet. Okay. So what is Then the problem now in terms of Lagrangian, so it is half x dot square plus y dot square plus gy, and my constraint is x square plus y square equals L square. So this is the entire problem that I am going to solve. And straight away, because we already now know what is Lagrange method of undetermined multiplier, we have discussed. So what will be the Euler Lagrange equations now? So let me go back a little bit. So these are my Euler Lagrange equations. So I have only one constraint equation, so I have only one lambda. So I have ddt of, I have two coordinates, so I'll have two equations. So del L del x dot equals del L del x. Now I have lambda del phi del x. So here, this equation I should write, del phi del x here. I should write this equation as minus L square equals 0. So that is my phi as a function of x and y. I have only one constant, one phi. Okay. And then the other equation will be, so again, let me keep this a little bit, little bit on left. So this equation, what is this equation going to be? This equation is, so ddt of del L del x dot is what? Ddt of del L del x dot is x dot x double dot, that is equals to del L del x. There is no x dependence, so del L del x is not there, plus lambda del phi del x, well that is there, so del phi del x is 2x, right? So this is 2 lambda x. Remember, lambda is a function of x and y. I will have another equation here. That will be equals del L del y plus lambda del phi del y. And what did I get? Once I work that out, I will guess y double dot in the left hand side, in the right hand side. Now I have something which depends on lambda, so I'll get a g, and then from the constraint I will get 2 lambda y. Okay, so you see, in this case we know what is the external force. The external force is only g, so we can directly read out the constraint force. This is just for understanding. The constraint force is here what? The constraint force F constraint is 2 lambda x x cap plus y y cap. Is this part in x direction, this part in y direction. This is acceleration in x, acceleration in y. Mass is 1 in our case. So this is the constraint force. Okay. Now I have to figure out what is lambda. You can do it with the usual method that we have discussed earlier. So it is from one of these equations you can figure out what is lambda. But let me do it in a little different way here. So what I do is, I have these two, I multiply this as x and this as y. So I get x double dot, and then I add them, so I get x double dot plus y double dot, and so I have multiplied this with x, so I get 2 lambda x square. I have multiplied this with y, so I get 2 lambda y square plus gy. And you immediately see in the right hand side, x square plus y square, I can write L square for that. That is where I can use one of the constraints. Right, so x double dot plus y double dot is this, and I can write now lambda in terms of everything else, and that will look a little complicated. X double dot plus y double dot minus gy by 2L square. Fine. So far so good, but you see lambda is still not in terms of x and y, so I have to somehow reduce x double dot and y double dot from this. So what I do is I have the constraint. See, I am doing trickery here, but anyway. So this is minus L square equals 0. I take double derivative of this. If I take the first derivative, I get x dot plus y dot is 0. If I take the second derivative, I get x double dot plus x dot square plus y double dot plus y dot square equals 0, right? So now I can write lambda as, instead of this here, I can write them as x dot square plus y dot square with a negative sign, so all can be negative, gy by 2l square. Well, this is good enough. I can actually solve for this, for x dot and y dot, if I have initial conditions and all, but this is good enough. I can put this lambda back to my original equation, which is here. So I can put lambda back here, and I'm not doing the rest of the exercise that is left for you to do. So what you do is you put lambda back here. So let me at least do that. So x double dot is 2 lambda x. So I have 2 minus x dot square plus y dot square plus gy by 2l square, and y double dot is 2 lambda y. So actually this 2 will cancel out, so I will get minus y by l square x dot square plus y dot square plus gy, and then I will have a g along with it, right? Now after that you have to solve these two equations. These are two differential equations of second order. Obviously we will need two initial conditions. For the pendulum, you know what are the two initial conditions, and try to solve for them. So what you should check now is that the pendulum equations in terms of x and y are the same as what you have got here, and that will give you a confidence that this method works. All right, that's it for today. Thank you.